Hi class, welcome to lesson 16, the final lesson on calculating heat. In this lesson, you will describe the keywords that indicate which heat equation to use in a calculation, solve heat equations for temperature changes, and differentiate between potential and kinetic energy changes on a phase change diagram. So recall that there are three equations for calculating heat found on the very back of your reference table T. In the previous lesson, we discussed how to calculate the heat energy for phase changes that occur at the plateaus. In today's lesson, we're going to talk about how to calculate heat for the temperature changes. We'll always use the equation Q equals mc delta T when there is a temperature change. The temperature change is represented by the sloped portions of the phase change diagram. So you're going to add these to the notes that you took in lesson number 15 and add this final column. That way, all of your notes for calculating heat are in one nice organized table. So again, when there's a temperature change, we're going to use Q equals mc delta T. And just like the previous heat equations, one variable always comes from reference table B. So take a minute to look at reference table B and find out what the specific heat capacity of water is and record it here in your notes. The keywords that you're going to look for in the word problem that will tell you that you should be using this equation, Q equals mc delta T, include words like temperature change, temperature increased, temperature decreased, the initial or starting temperature, final temperature, ending temperature, from blank degrees Celsius to blank degrees Celsius, warms or cools. If you see any of these words in a word problem, you know you should use the equation Q equals mc delta T. For each word problem or heat calculation, we are going to be using one of three formulas. These formulas are found on reference table T. Reference table T has to be used in conjunction with reference table B, as each equation has a constant found on reference table B. That constant is underlined here in red. It is either C, the specific heat capacity of water, H sub V, the heat of vaporization, or HF, the heat of fusion. You can see on the phase change diagram where we only have one phase, that is where the temperature changes. So that's where we could use Q equals mc delta T. Before we solve any heat equations, let's look at the factors that affect the change in temperature. The first factor is mass. If we try to heat up both of these beakers on the same hot plate or stove, obviously the beaker with less mass will change temperature faster than the beaker with more mass. Another important factor that influences how quickly something heats or cools is the intermolecular forces that are found in the substance. This important physical property can be seen in your kitchen. When heating up water and oil, one should note that oil will get hotter much faster than water, and you should use great caution when cooking with oil, as since it can get hotter than water, it can cause more severe burns than water. Now, C, which stands for specific heat capacity, is defined as the heat needed to raise the temperature of 1 gram of substance 1 degree Celsius. I think of heat capacity as the heat bank of a substance. So something like a metal has a very low heat capacity. it cannot hold much heat inside of it. So when we continually add heat to it, it quickly fills with heat and all the excess heat is felt on the outside. So a substance with a small specific heat capacity heats up and cools down very quickly. But a substance with a very high specific heat capacity, like water, will heat up and cool down very slowly because it stores a lot of heat within the substance. It has a very large heat bank.
Specific heat capacity measures how quickly a substance heats up or cools down. A substance with a small specific heat capacity, like the liquid metal mercury, heats up and cools down very quickly, while a substance with a much larger specific heat capacity that you can see here, like that of water, will heat up and cool down very slowly. So when we break these questions down to simpler steps, they're really easy to do. First off, delta T is the final temperature minus the initial temperature. So when we do this practice problem, and a calorimeter, or a device that measures changes in heat, contains a solution at 93 Celsius and it cools to 34. If we subtract 34, the final temperature, from 93, we'll get a negative number, indicating that heat is lost. So this corresponds with an exothermic reaction. In the next example, we are looking for the delta T when the temperature outside is -5 and the temperature inside is 32. If we take the final temperature minus the initial temperature, you'll see that we'll have a positive value. This positive value means that this temperature change corresponds with an endothermic reaction where heat is added. Let's do some more practice problems. In this practice problem, we are calculating the amount of heat in joules 32 grams of liquid water absorb when it is heated from 25 degrees Celsius to 80 degrees Celsius. The first thing that you must always do is set up a variable table. So here we're looking for Q, which is heat. So we can assign this the variable X. We are given the mass and the change in temperature. Remember, one value is always coming from reference table B. That is the specific heat capacity. Once we substitute, all we have to do is use our calculator to solve. Notice that this is an endothermic reaction as represented by its positive delta H. In this example, a lump of silver has a heat capacity of 42 joules and a mass of 181 grams. The change in temperature is 25. The first thing you must do is set up a variable table. We are given heat, mass, and the change in temperature. Because we are not dealing with water, we cannot use this heat capacity of 4.18. We substitute and solve. Notice that silver has a very small heat capacity, meaning it quickly heats up.
Let's try this practice problem. How much heat is needed to bring 25-gram sample of water from an initial temperature of 20 degrees Celsius to 60 degrees Celsius? So here we see the keyword initial temperature and 1 degree Celsius to another degree Celsius. In this case, 20 degrees Celsius to 65 degrees Celsius. So we're going to use the equation Q equals mc delta T. We're going to substitute, we're going to solve, and then we're going to round our answer to the correct number of significant digits. This concludes lesson number 16, calculating heat for temperature changes. Make sure you've taken good notes. Write down any questions you have and bring them to class. We will discuss them if you ask them. Complete your homework on Google Classroom and put your reference table and calculator back in your backpack so that you're prepared for class. I'll see you soon.